Well, thank you, David. And from Danny and I, good morning, good afternoon, and good evening. I'm coming to you live from Carlsbad, California, which is where our facility is that manufactures the microwave absorbing materials, as well as the conductive elastomers, as well as some of the dielectric and radome materials. So as David said, today's talk, it's a little bit different. We're not just going to talk about our products, but more about some of the testing and issues. So if you will go to the table of contents. So when you're designing in these EMI materials, you're mainly thinking of obviously the electrical problems you have, but what tends to happen is the real world creeps in, and where you're going to use them, how you're going to use them, as much as a factor as is solving the EMI problem. So we're just going to go through some of the issues. I've been involved with absorbing materials for sure and ECE gaskets for a long time. And as part of that, it's always a consideration. And Danny will then go into some of the metals issues, which have similar types of issues, or maybe a little bit different. But in one case, you're dealing with polymers and with magnetic or other types of fillers. In the other case, you're dealing with structural metals. But this is kind of what we're going to go through. Some of the issues that we need to worry about, some of the testing methodologies, and then the various materials. So first of all, these are the kind of the three areas we're going to go into, as David said. Microwave absorbers. Absorbers are used a lot of times on the outside of things, vehicles, around antennas, inside of housings, and so definitely is an area that they receive a lot of attention as far as environmental concerns. And then the same with conductive elastomers. They actually have a little different problem in that they're almost in the middle of a battery cell. So you have different metals compatibilities that cause corrosion issues there, as well as general environment. And then on metals, which Danny will talk about a little, things like fatigue, shock, vibration, corrosion, those are all issues that confront our metals. But really, we deal at Laird across the board in a lot of different applications. And I'm showing you a lot of military applications or aerospace applications, but indeed, we do a lot of work in the automotive segment, and they face very similar problems. We're getting more and more involved in industrial applications and the Internet of Things and smart applications. And so there's a lot of rigorous environments out there that you need to be aware of, and there are solutions available, and you just need to be mindful of those. So in my experience, the two biggest problems we run into are exposure to fluids and then corrosion. Corrosion really across the board, everything corrodes, almost no matter what it is. So two different areas, there's standard testing for it. You're looking at in the upper left-hand corner, salt fog chamber. And so basically what you create is a warm fog atmosphere of a saline solution, which then you immerse the material in. It could be by itself, it could be in situ with something else. So there's a couple different ways to test it. But if you look at that lower left-hand corner, you can really see the problem. This is standard carbonyl iron loaded rubber. And after only 3 days in a salt fog chamber, you can see the level of corrosion. So the standard filler for these magnetic absorbers is carbonyl iron powder, and it's pure iron, and so it will oxidize. And when it oxidizes, two things happen. One is it looks like you see in that picture, which isn't very pretty, but two, iron oxide is not magnetic. And so you've got two problems. One is a cosmetic problem, but more importantly, as it continues to rust, the performance of the absorber will degrade. So that's just general corrosion of filler materials. On the right, you're going to see something a little bit different. So with, again, as I said, with ECE, you've got a rubber gasket loaded with metal in between, most likely two metal or composite plates. So what you've got is a galvanic compatibility issue. And basically in a salt and water environment, you're creating, that's a nice solution to conduct ions or electrons. You're creating basically a battery cell. So depending on the properties of the filler in the elastomer and then the properties of the metal it's going against, you can have metal ions acting as an anode and moving towards this and causing corrosion. So what this table shows is kind of two different things. It shows different metals, which would be the interface material, and then different types of conductive elastomers. And just to point out something, if you look at the chromated aluminum, which is a standard material that's used in a lot of applications. Obviously, you can see some of these materials, silver copper, silver nickel, have a very different electronegativity potential and will cause significant corrosion. The silver aluminum, so you have a silver coated aluminum particle, is actually very compatible. We take that one step further. We've offered a new product starting last year. It's called ECE 130 and 131, which are passivated silver aluminum. So now we put a passivated coating on, which continues to help that. If you look at the bottom, you can see stainless steel. That's certainly a good choice if you can use it, because that's pretty much compatible with anything. It doesn't corrode. But the other problem you have is you've got the metal corroding, but then the other problem is the filler inside can corrode as well. And when that happens, the way these conductive elastomers work is that they have what's called a percolation threshold. So you've got all these conductive particles touching, and that's what gives you the electrical path through the rubber material. As you start corroding those particles, you lose that connection and you start degrading the performance. So you've got to worry about, one, corroding the metal that you're trying to protect, and then two is losing the performance. So that's all about selecting the right filler and based on what your material is. We also released another product last year, again for corrosion resistance, ECE 134 and 135. It's a nickel aluminum filler and is the most resistant to corrosion that you can get. So we have some very corrosion resistant materials that we've just introduced. So if that is an issue, we definitely have some new solutions to look at. Okay, as I said, corrosion number one, probably fluid number two. These materials tend to get used on vehicles, could it be an auto, but there's engine oils. This is a standard test matrix per mil standard 810 method 504, but you're talking about fuel. JP8 fuel is standard fuel for fighters. You talk about hydraulic fluids, a couple different types of oils, and then de-icing and antifreeze fluids as well. So all of these, usually the test is a soak test. You'll take the material, soak it in there at a certain temperature for a certain period of time, and you'll look at volume or mass swell of the material. And then of course you'll look at the performance of the material before and after. So those are kind of the two things. If the elastomer is going to be subject to swelling, or the polymer, due to incompatibility with these materials, and then that could also affect the performance of the filler inside. So a lot of fluid testing that we do, and we do this in-house as well as through subcontractors. Some other types of tests. So when we qualify our materials for a new program, a lot of times we'll go through a formal qualification program. And these qualification tests, we'll put together a test procedure, conduct the test either in-house or through subcontractors, and then write a final test report with the results. So some of the different testing we do, outgassing is certainly a big one for aerospace and space applications, where you're looking at, in a vacuum environment, what comes off of this material. So there's two usually things that are measured: the total mass loss, so how much weight is lost during this exposure, and then secondarily what are called CBCMs, condensable materials, that could then fog an optic. So usually in optical situations, in space situations where there's low, vacuum, high vacuum, that's a consideration. So we've done a lot of testing on our materials, And for the most part, the polymeric materials perform well and meet the ASTM requirements. Abrasion is a consideration. There's Tabor abrasion, which is a standard one, but it basically involves rubbing a known material against your material, looking at weight loss. So how tough is it, how abrasion resistant? And certainly if you're on the outside of something moving very quickly, abrasion resistance is an important consideration, or in areas like rain and hail. The high power test was something pretty unique. These absorbing materials, the way they work is they absorb the energy, electromagnetic energy, and turn it into heat. So normally in most environments, that's okay, that's not an issue. But what happens in certain applications where you're very close to high power antennas, and this could be on, say, a Navy ship or something, that heat up rate can become very important. So a lot of questions regard around how much heat, how much energy can it withstand? And so we usually talk about that in watts per square inch or watts per square centimeter. So what this test was basically a 15 gigahertz antenna cranked up to very high power, and we were trying to generate anywhere from 1 to 5 watts per square inch onto this honeycomb panel. It was an interesting test in the fact that we tested open-celled foam, which actually tested better than the honeycomb. The honeycomb was mounted on a conductive ground plane, so there was a backing to it. And if you know honeycomb, it's basically consists of little cells which almost acted as heat pipes. And so even at like 1 watt per square inch, this started getting very, very hot, up to about 400 degrees, and we terminated the test. So it was certainly airflow is a very big consideration in how these things can handle heat. The bottom row, just some other tests. We do solar testing. These are standard 810 tests, impinging rain and blowing sand and dust. Other tests, we do fungus is generally a consideration. Certainly temperature cycling and humidity are always tests that are run, and then ozone testing as well. A lot of testing we do in-house. We do particle size analysis. The middle picture there on the top is thermogravimetric and differential scanning calorimetry. That is a good test to look at these materials and how they, it's kind of weight loss versus heating. And so you can kind of see how these things do at elevated temperatures. And what we found is when we're looking for things up at higher temperatures, and we're looking at trying to come up with 600-degree Fahrenheit solutions for people, that this long-term weight loss, that the TGA can give us is a very good way to kind of look at different materials and compare their performance. We certainly do mechanical testing, tensile elongation, tear. As I said earlier, environmental cycling and humidity testing is very important. And then for the radome work we're doing a lot of impact testing. So we're evaluating new thermoplastics. We're adding tougheners to them to improve the abrasion or the impact resistance. We're worried about hail strike. We're worried about rain for these radomes, and so the performance of those under an impact load is very important. It's in a very dramatic test too. If you get something that breaks when that it's a 500-gram ball that drops on the panel from anywhere from 1.5 to 2 meters, and if it shatters, it can create a mess. And then I'm going to talk about electromagnetics because that's really the proof. You do your testing and you measure or you take it through an environmental constraint and then you remeasure it. So certainly in the end, no matter what the environmental action is, we want to make sure the material still works. So we have a variety of ways to test low dielectric materials, low frequency materials, and up to 90 gigahertz as well. So we'll do a lot of evaluations on material, heat, humidity, and then retest for electrical performance. Okay, so we're going to talk a little bit about absorbers first, and we're going to talk about magnetic ones since I showed you that dramatic picture of the corrosion issues that they have. So you're looking at two things again. You're looking at the polymer or the elastomer, and then you're looking at the filler. So the ones that we recommend, our standard product line, our standard commercial product line is silicone, just standard silicone, which is a great material to use, but it does not withstand things like solvents. It's poor in fluid resistance. So we've qualified nitrile rubber as a very fuel resistant. It's got a good temperature range to 280F. Easy to bond and paint, so you can be bonded with standard epoxies or urethane adhesives. Standard paints adhere well to it, which are also issues for silicone-based ones. So that's a good standard general material that meets all the fuel resistant requirements that you'll have. For higher temperatures, and we're doing a lot of work with fluorosilicones, both in conductive elastomers and absorbers, where we've actually released a series of absorbers in fluorosilicone, but you have good fuel resistance again versus silicones, and then temperature ranges up to 475 to 500 degrees Fahrenheit. So a higher temperature solution, and again, they're usually bonded with either silicone or fluorosilicone adhesives, but have good affinity to that. They're certainly used on the exterior vehicles and in large quantity production settings. Fluoroelastomers are a little different. That's things like Viton. They're also fuel resistant, got a good temperature range as well, but then also a lot tougher than the fluorosilicones, which are softer, and they've got good abrasion resistance. So if you have a rain erosion issue or an abrasion issue, the Viton is really a good all-around material. And then I bring up silicones only because we have standard silicones, but we're now working on silicones that can get up to 600 degrees Fahrenheit. And so we're kind of doing some interesting work, and that's where we use the TGA to kind of evaluate these high temperature materials over time and their weight loss. So those are the elastomers. Then the filler. Okay, so I said carbonyl iron powder, standard filler, prone to corrosion for sure. So what we use is a material called iron silicide. This is an iron silicon alloy, which is non-corrosive, so it will not rust. They use a lot in Navy applications and qualified in a number of applications. And it's available in different form factors. And that's where there's a lot of work being done on changing particle morphology and shape, annealing temperatures, aspect ratio to improve performance. And the third area, which we are doing a lot of work in over the past year, has been in looking at other alloys. So things like stainless steel can be used, chromium-based alloys, sendust, which is a low-frequency material. Those are all available, and we've done a lot of work in releasing products with some of these new fillers because a lot of them will have much better corrosion resistance than standard iron. Those pictures there, that's a large compression molding press. And then you can see some of the detailed parts. That lower right picture is actually a Viton edge lip. The Viton was chosen for its high temperature and the abrasion resistance that it has. And it was some modeling we did to manufacture that part. That lower left is a gasket, a dual blade seal gasket, and then some unique shape parts. So we can mold specific shapes with these materials to meet your exact requirements. I'm segueing into this because I think it's important. We're releasing a new product. It's called RFLW, but basically talking about particle shape and morphology, we've taken this iron silicide type based filler, but with a much different particle shape. And what we found is we've got a series of products which have a much higher permeability and permittivity than our standard iron products. So one is it's good for low frequency applications. Two, it weighs less because you use less of it. And three, it meets the ASTM B117 salt fog. So for low frequency corrosion solutions, we have a new answer, which we're releasing to people and getting a lot of interest in. And these two graphs kind of show you a little bit of the advantages. BSR1 and MCS, that's the black and red curve. This is attenuation, which is calculated from the permeability and permittivity of a material. So how much energy is attenuated as it goes through. And you can see that versus frequency. Certainly as wavelengths get shorter at higher frequencies, attenuation increases. But now if you look at the LW30 and 40, and that's 30 and 40 volume percent loading, what you can see is much higher attenuation level. So the other advantage of it here is a tuned material at 1.4 gigahertz, very low frequency, GPS frequency. You can see our standard BSR1 would be 200 thou thick. When we go to RFLW 40, you're at 80 thou thick, so over 50% thickness reduction. So that's some of the advantage of this material. So low frequency, corrosion resistant, a new solution. Okay, so the other type of absorber that we have are foam-based materials. Foams are great, they're cheaper, they're lightweight, they're very broadband, they have terrible resistance to environment. So what do? We take these foams, we take their good properties, and then what we do is we try to find ways to protect them. And so that the different types of absorbers we have, the AN, which are the multi-layer foams, we have these reticulated foams that are very open-celled and we can continuously grade them. So what do we do with them? We cover them. So we take ANW, which is the foam covered with a material called Coverlite. It's a reinforced thin fabric. Both Humaseal or Humaseal and Searseal are sprayable coatings, which for either dust arrestants or for moisture. So that lower right-hand picture is a picture of AN foam, water jet cut to a specific shape, and then subsequently sprayed and treated with this Searseal material, which acts as a good water penetration mitigator. Blankets, so that lower left-hand picture, we'll take this and we'll sew it into custom blankets that can be form-fit to customers' applications. And then filling reticulated foam. So that upper left-hand picture is open-celled foam, that's the absorber, subsequently filled with a closed-celled rigid foam. So you've got kind of a structural foam material there that's an absorbing foam. So those, and that can be molded and machined into different shapes. So these are some of the ways that we work with our foam materials to provide protection against environment. We'll talk about ECE and then we'll go to Danny. So same thing, you've got elastomers, you've got fillers. The choice in elastomers is relatively straightforward. Silicones are really good for gaskets. They're soft, they're resilient, they've got good compressibility. Silicones, not good for fuel. So you have silicones for standard applications, fluorosilicones for fuel resistant applications. We also have a material called EPDM. That's used a lot in very specific applications. So for Army vehicles, you'll get exposed to what's called NBC, nuclear, biological, chemical contamination. That's bad enough, but then the way you wash down the vehicle is with very caustic solutions. And this EPDM can handle those caustic solutions. So if you have an application that is going to see a potential NBC exposure, we do have a solution for that. Fillers, nickel graphite. We use a lot of that, and it's very good in composite applications. So if you're going against a graphite structure as a gasket, then the nickel graphite is very good, has a good affinity to that, very little corrosion. And then, like I said before, the other fillers are usually silver coated because of its really good conductivity, but then you'll use a base material, one, to reduce cost, and two, for better galvanic compatibility. So we have silver coated nickel, copper, aluminum, and glass, and I touted the silver coated aluminum. That's probably the one that we sell the most of because of so many aluminum housings that are being used for. And then we just came up with two new corrosion resistant materials, which include a passivated silver aluminum and a nickel aluminum. And the nickel aluminum is probably the best for corrosion resistance. One last thing on that, because again, we talk about resistance, to external environments, but also there's the mechanical resistance. And one of the things that we always tout is using this Abacus finite element analysis software, our ability to really look at things like, strain and stress, cycling, which leads to fatigue, coefficient of friction, which is important in any kind of gasket application. So we do a lot of analysis on the mechanical properties, and that upper left-hand corner is a dual blade seal, which was really developed for a very rigorous environment. It sees 10 psi of pressure from the internal and the external, so we needed a dual seal, and then its environment went through every one of those tests I've talked about so far. So we get involved in a lot of rigorous applications, and using this analysis software really helps us to hone in on the best designs. I just mentioned Radomes, not a lot here, but we do a lot of impact testing on our Radomes and our Radome materials. We're looking at, I think the innovations we're trying to make there, we're using polymer-based fibers, so things like Spectra and Inegro, which is a polypropylene fiber. Spectra is a high-density polyethylene fiber. They're low dielectric, so they're good for Radomes, but they're also very tough and offer you good impact resistance. So that's what a lot of our work has been done, kind of looking at high frequency, very low dielectric constant Radomes. And then we also do a lot for submarine applications, and so we do have the ability to test for hydrostatic pressures up to 1050. So you don't want, obviously, your Radome to absorb water, because water has a very high dielectric constant, and so the Radome will no longer work properly. So a little bit on that, and now I'm going to turn to my colleague, Mr. Ramirez, to talk a little bit about some of our precision metal applications and some of the work we do in that area.
Thank you, Rick. So kind of piggybacking on what Rick's been talking about, Abacus and the software we do with metals, it's the same thing. It's rigorous. It's really dependent on the materials, the application that's utilized. And so we work with an array of metals, copper alloys, spring steels, carbon steels, to help address customer concerns. And with that, you run into challenges in environment, moisture, humidity, altitude, temperatures, where you could utilize platings to help protect that material. Here on the bottom picture, you see an example of a customer using a traditional board level shield, running through our soft wall testing, and able to add a nickel underplate to help improve the corrosion resistance of that shield. Also, an alternative is changing that material to a nickel silver, where you still have that reflow solderability capabilities with that material, but now a lot highly corrosive resistance. With these platings, it's also with performance, but also the capability, the way it can perceive, like a nickel plating. It's a lot better for abrasion, for shear processing plating versus a tin. It's softer, it's a lot more harder, so you get that better resistance to the customer's product for reliability. Also with stainless steels, we have the ability to do passivation to help improve on the corrosion resistance of that material. That's done in-house. And then to the right is fatigue analysis. Here, we do the same Abacus software, run analysis to our customers so they can understand how their product is going to survive in their applications. So here, you're looking at the number of cycles at a specific compressed height and how long it would last. And here it gives the customer the visibility to know ahead of time if there needs to be tweaks, some modifications, changes in materials, tensils, elongation on materials to help achieve a more ruggedized solution for the customer. Next slide, Rick.
Oh, I got to play them.
So here on the left is a shock and vibration analysis that we've done. We call it the time squared ball drop. Here, the customer really wanted to understand how their application was going to behave at 100-gram load dropping onto the unit and with the components underneath, the impacts of it. So there you see in that video just a simulation, understanding, okay, well, there's going to be some residual stress on certain locations onto the part, but within some modifications of design, we're able to make a more ruggedized solution for the customer to meet their needs and their requirements. And based on those type of analysis, the point on the right, the mechanical strength and durability, these are things that we've done We could have the capability to doing deep draw solutions to help make the part more ruggedized and still achieve that EMI functionality by eliminating the apertures on the part. The one in the upper right-hand corner with the circle is a rigid corner. This is a more traditional improvement on a traditional folded board level shield where you have some overlap. Here you're doing a half draw and closing up that seam to help improve the shielding effectiveness. On top of that is making it more robust, so improving the flatness and the structural preference of the shield itself, that part. And then on the lower left-hand corner, we see patent pending PCB. This is a through-hole lock feature. What you have here is design improvement. So the customer had a shock and vibe environment, specifically in the automotive segment, where they needed to pass some ruggedized testing. So they couldn't really just depend on the solder reflow part being soldered onto the board to adhere to pass their testing. So what we were able to do is add some mechanical features into the product where these fingers clamped into onto the board to help add extra protection so they can pass the needs in their environment. And then to the lower right, you see here is just a simple dimple D-snap. Traditionally, you see on two-piece board level shields, a simple dimple hook on over, layover to a frame, but you could run into some issues there. So to help improve on that, we ended up shearing half that dimple to create a snapping feature. So once you had that cover onto that frame, you had a lot more security of that cover being adhered to that frame a lot more with a lot more strength versus your traditional dimples that you see out there in the market. So what you're seeing here is just analysis to how we can make our products more robust to address the customer's needs out there in the market. So just examples that we have here.
Thank you, Danny. That was good. Appreciate it. And then, yeah, so I think the takeaway is what you've seen here is this is what we can do. We can develop ruggedized solutions. We've done that. We have a lot of ideas. We have good engineering and good test capabilities to do that. So don't be afraid of a rugged atmosphere. Embrace it, and we will help you solve your problems. We have over the, kind of over the past year, especially in the mil-aero sector, released a number of products that have been more rugged. We talk about a heat and fuel resistant product line. That's some of our fluorosilicone work we've done. Some of these galvanic corrosion resistant ECEs, again, a couple products we've released. And so we are and then protecting the foam. We've done a lot of work on that. So I do it. We can check our website out. I think this will actually be available on it afterwards, but feel free to ask questions, to reach out to us. Danny and I, we do love to ham and egg it and do presentations to different groups. So if you want to get a follow-up presentation on your application, please get a hold of us and we would be happy to do that. So for that, I thank you for your time. I guess, David, you're going to come back on, but if you do have questions, type them in the window. Not sure if there's anything we can address now, or we will definitely get back to you with answers, but thank you. I appreciate it.